All right, welcome. So in this video I want to start talking about collisions, and specifically I want to talk about collision detection using some of our most standard ways of doing collision detection using a bounding circle or a bounding box. And really when we are talking about collisions, there's really two important things we need to do. One is first, can we just detect if a collision occurs? And then the second part, which tends to get a little bit more muddy, is what do we do once we've detected that a collision has occurred? And we call this collision handling. So you've probably maybe heard of both these terms, maybe used somewhat interchangeably, collision detection, collision handling. While they're really sort of two sides of the same coin or two pieces of the same puzzle, we need to use both of them to do whatever it is that we need to do. But in the actual programmatic part, we usually split these into two different phases, if you will. Collision detection, and then once we've detected a collision, collision handling. Now the other thing that I will bring up is related to collision detection is collision detection can be a fairly inefficient operation to carry out in our game, and the reason for that is, let's just take a look down here at what I'm calling the narrow phase of collision detection, is where we're going to take any two elements and we're going to do a pairwise check between those entities to see if they collide. So imagine you've got a number of entities in your game. You want to know if any of them are colliding. You're going to pick two out, which is a pair, and then run whatever math you need to do to check to see if they've collided. Handle that collision if you need to, and then hand those two back. Pick another two out. So we're going to be picking pairs, and we're going to try and do this detection for all pairs to see if any collisions occur. And of course, when you're doing an all pairs type check, you end up with a big O of n squared number of pairs that you're going to need to check if you started out with n entities. And because of this, a lot of what we're doing in our normal game updates is going to be linear in the number of entities. For each entity, we have to do one thing or a handful of things. But when we start doing these pairwise checks necessary for collision, we're going to say for each entity, we now need to compare it to every other entity. So that's going to increase the cost of these operations. And as a result, this is often going to be the most costly thing that you're going to be doing in your updates. If you happen to be doing these collision detections, this might be one of the more costly operations. As a result, we tend to want to reduce the number of collision detection operations we need to do, meaning we might want to reduce the number of entities that we need to compare between. And so often we'll do that in an earlier phase, which we'll call a broad phase, where we try and eliminate checks that we don't need to make. And there's a couple of simple and obvious ways to do this. The first one is sometimes there are certain types of entities that just don't need to know about collisions at all, or they only need to know about collisions with a small group of other entities. So for example, in my Super Mario Brothers game, there are background images like hills and trees and bushes and clouds that don't interact with anything. Even though Mario can collide with them or walk in front of them, for instance, there's no programmatic effect, there's no functional effect of that collision, so we just ignore those collisions altogether. We don't need to do collision detection with those background elements. Now in my game I actually still do them, and that's because the narrow phase for me is not so costly that that I need a broad phase to eliminate those checks. But if I got to a case where I had so many entities that was indeed becoming costly, the first thing I might do is just say, well, let's separate all my background entities out as a separate kind of entities that don't need to participate in collision detection. And then once they've been separated out, my N basically has been reduced by however many background entities. Now there are also other kind of entities like platforms, for instance, that are important for collision. Mario might land on them, other entities might land on them as well. But platforms usually, at least in Mario, don't interact with each other. The platforms themselves usually are stationary, at least in most of the levels, which means there's no chance of them moving and colliding into another platform. So for another reason, in our broad phase, we might say, okay, take all our platforms out, put them in their own separate list of platforms. I will need to check against them when I may be looking for landing for Mario or other entities, but the platforms themselves don't need to check to see if they've collided with other platforms, for instance. And that's another broad phase type of simplification you might put in here. And then finally, and this is common in modern games that are maybe more computationally intensive, where you might have thousands of entities and you maybe need to do collision detection between all of them, that becomes very, very computationally intensive when we do an n squared on that. We're now into millions of computations. And so another thing we might do in a broad phase is what we might call chunking, where we're going to break the entire environment down into smaller chunks, which we might think of as a grid cell, or if it's 3D, it's sort of a cube. And then what we're going to do is we're going to do our narrow phase within a chunk, but then roughly between two chunks, we're going to say, hey, entities between two chunks, as long as they don't share a border, are just too far apart to be colliding. So we'll never have to compare an entity in a distant chunk to an entity in this chunk. And what that does is it reduces the n from the n of all of our entities, maybe we have thousands of entities, down to the number of entities just within that chunk. And therefore maybe we cut that down by some order of magnitude, maybe going from 1,000 entities down to 100 entities. And now when we square that, we're actually getting a considerable amount of savings, because 1,000 squared would be 1,000,000, but 100 squared is only 10,000. So we actually are taking a cost that maybe was 1,000 times more expensive before and making it only 10 times more expensive now. And that's going to be, again, one of the benefits of doing a broad phase. Now, if you're using this to develop your own games and you're following my standard, doing sort of a 2D simple kind of platforming, maybe an old school type of game like Super Mario Brothers, then you're very likely not going to need a broad phase, or you're not going to need chunking. But you might do, like I mentioned, some simplified broad phase where you're going to just eliminate, say, platform versus platform collisions or other collisions that you just know are not going to be needed to be checked. Like I said, with that said, my own version right now has no broad phase. I am purely a narrow phase because my n is small enough that my n squared here is not costly. And that's, again, what you should probably do in your own game if you don't have too many entities. Why? Because it's just simpler. We don't have to build in the broad phase. There's no code associated with that at all. So the only code we need to worry about is the narrow phase. Okay, so now we've just talked at a high level a little bit about what collision detection is and how we might carry it out. Now let's go and look into the actual math of what we're going to do when we carry out our collision detection. So the first thing that I want to do is when we're talking about a collision with Mario. Now what I've got here is a sort of the image of Mario jumping, which is, again, a very simple image. Now what we might technically want to know is, say Mario's jumping up here and we want to see if he hits a brick. We might actually want to know if these pixels actually run into the pixels of a brick. Or maybe these pixels over here, or maybe if he's landing, if this little heel pixel hits the platform, then he can land. Now that is very, very fine-tuned or fine-grained even collision detection there. This is what we might call pixel-to-pixel collisions. Now some games rely on pixel-to-pixel collisions, but pixel-to-pixel collisions can be incredibly costly or expensive to compute. And so most games, especially in the old days when we didn't have the time to compute those costly computations, we tried to use a different means for doing collisions. So instead, what we'll do is we'll draw some kind of shape around our entity, and that shape we'll call a bounding shape. It's a bounding shape, so it should encapsulate the whole entity, but I'll mention in a minute why we might not encapsulate the whole entity as well. So in this case, I've drawn a circle, which we could call a bounding circle, around Mario. And then the idea would be, if anything collides with this circle, we'll just say that it collides with Mario, which means we might get a little bit of bizarre, this empty space here we run into an entity here, and we're going to say that that's going to trigger a collision with Mario. Well, we can always change the size of this circle if we like, make it larger or smaller. That's one of the reasons why we're going to make a bounding circle. It's going to be separate from the actual shape or size of the image we're drawing there, so we can make it smaller or larger so we can balance the way our collisions work in our game. Now in this case, I've just simply made my bounding circle around him. I haven't really put a lot of effort into fine-tuning this because I didn't actually use a bounding circle in Mario. This is mostly just for demonstration. Now when we state a bounding circle, probably not surprisingly, we state it with sort of 3 coordinates or 3 different parameters. First, the x and the y, which is going to be the center point. We give circles by center points, and then the radius, just how wide is the circle, or what is the length of our radius. So if we use bounding circles in our game for collisions, then we're just going to draw a circle around every single entity that needs to be considered for collisions, and then we're just going to handle collisions between those circles instead of between the entities themselves. So the beauty of using bounding circles for our collision detection is that the math and logic involved in detecting if 2 bounding circles are colliding is actually very trivial, very simple. And we can see this very easily with just this simple diagram that I've got here. I've got 3 different examples of circles colliding, not colliding, and maybe an edge case where they're touching right on the edge here. And we can see that this logic that I've got here, it says that 2 circles will intersect if the distance between their center points is less than the sum of their radii. Now, luckily, this is very lucky for us because the storing of bounding circles means storing their center points and storing their radii. So we have all the information we need in our bounding circles to do this little bit of logic. We just need to do this distance calculation using a Pythagorean theorem. So we'll take our 2 points and we'll calculate the distance between them. That will give us this green line that I've got in my diagram here. The green line is the distance between their centers. And then what I'll do is I'll sum their radii, which I've got here. The 2 red lines are the length of the radii for my 2 circles. And we can quite clearly see in this example here that the green line is greater than the sum of the red lines. And therefore, this is not an intersect because the distance between our center points is, in this case, greater than the sum of their radii. Again, this was an edge case where in our handling, we have to decide, is this a collision or not? Do we permit this or not? And in a lot of cases, I say I do permit this. A little touching is okay, but no overlap. Okay, so in this case, this is the edge case because this is a case where the distance between their center points is exactly equal to the sum of their radii. And so this logic I've got here says the collision only occurs if it's less than, I guess I could put in brackets here, or equal to, because that's the edge case we need to decide. Do we want to include this as a collision or not? And then this is the obvious case of a collision where the distance between the 2 center points now is obviously less than the sum of their 2 radii. I've had to push the radii out a little bit here to see what the sum of the 2 radii would actually look like, since it is longer than the distance between the 2 center points here. And so this would be a case of an intersection or a collision between our 2 circles. Now, like I mentioned, the logic to do this, here I've just made simple logic. I actually haven't used circle-circle collision in my Super Mario Brothers, so this is just some simple circle-circle collision logic that I created for a separate demo. But this is going to be very simplistic. I haven't built this into a class, for instance, but say we've got these 2 circles defined by their radius and their x and their y coordinates. And then what I'm going to do here is the logic that I need to do to actually check to see if there's going to be a collision. So as I mentioned, there's really not too much I need to do here. I need to sum my radii. That's what I'm doing down here in the actual check, taking the sum of my 2 radii. And then I just need to do the distance between my 2 center points of my circle. And I'm doing that here by doing first the simple distance calculation and then doing Pythagoras by squaring the distances, summing them, and then taking the square root. So that's Pythagoras. That gives me the distance. Check to see if the distance is less than the sum of the radius. If it is, boom, we've got a collision. So here I've just got a comment that says collision detected, because what happens here is this is where we put the collision handling logic. And I'm going to leave that to a different topic. So if you're interested in using circles or bounding circles in your game, then this is the logic that you need. It's very simple. Feel free to copy this or refactor this into your own bounding circle class so that you can do circle-circle collisions and check to see when two circles collide. Circle-circle collisions were very common in some of the earliest games, even before the Nintendo Entertainment System, like the Atari system, for a very classic game like Asteroids. If you remember the Asteroids game where you're this little ship, you fly around and rocks are flying all around you. The rocks are circles, the ship is a circle, and you shoot little circles as well. And the circle-circle collision is all you needed in that game to do simple collision detection and handling for, again, some of those early games. But circles have their limitations, and so in some of the more modern games, they switched to boxes or rectangles. But not just any old rectangle or any old box, because those can be a little bit arbitrary and hard to deal with. So instead what we're creating is what we call axis-aligned bounding boxes. Axis-aligned meaning aligning the box to the axis. So we have our X and our Y axis, which is normally our horizontal and vertical axis. Assuming no bizarre rotations or polar coordinates or something else going on here, we're just going to create a rectangle that would just sit nicely there, say on the X axis. It would rest there because its axis is aligned. With an axis-aligned bounding box, we actually only need two of the corners. If we were going to describe a normal, possibly rotated rectangle, then we would need to have all four corner points, okay? But for an axis-aligned bounding box, we can get away with just two corners, technically, but usually the way that we like to state this, because this is common in a lot of our rectangle descriptions, say drawing a rectangle on the canvas, we do it this way as well. We have the X and the Y, that's going to be the top left corner of our bounding box. But then instead of stating the bottom right corner, we actually just state the width and the height. So we could calculate the bottom right corner with by doing a sum of both of those, the X plus the width and the Y plus the height. One thing you'll notice here that at least around Mario, the way I've drawn it, there's a lot less sort of empty space in this, and this is because the frame that we drew Mario on was also a square. And so this is one reason why axis-aligned bounding boxes became more popular. Since the frames of the images that we were animating were usually themselves rectangles, it was convenient to draw a rectangle around that frame. And in fact, probably in the original Mario, they didn't actually use a bounding box at all. They might have used the frame itself, the dimensions of the frame itself. Actually, now that I think about that, in the original Mario Brothers, they do allow a little bit of overlap. So it's true that probably in the original Mario Brothers, the actual bounding box around Mario might be smaller than this. So he allows a little bit of overlap, say with 1 pixel of his foot and his hand here before it counts as a collision. I'll show you again a little bit how I do that in my version of Super Mario Brothers. I actually leave Mario's bounding box alone. His bounding box is the size of his frame, but I changed the size of the bounding box of other entities he might encounter so as to, again, simulate as closely as possible the behavior of the original Super Mario Brothers. Now again, the logic or the math involved in detecting if two bounding boxes are overlapping is not particularly difficult. If we want to raise ourselves the question, okay, how do we determine if two boxes are intersecting? Same idea we just did with the circles. When would two circles be intersecting? Here we're saying, when would two boxes be intersecting? Now I sat down, this was a few years ago, and I thought, hey, I want to write this myself without doing any Googles, for instance, and I wanted to think about how could I determine what were all the different ways that two bounding boxes could intersect. And I came up with a number, and in fact, at first I came up with the first 4 in the middle here, which was the idea that maybe one of the corners of a box might be inside of the other box, and in so doing I could just do a simple check. It's pretty easy to check if a point is inside a box. That's pretty easy. So if I can discover that any of my corners is inside any of the other boxes, that means I clearly have a collision. And so that's what I thought. But then I started getting around and I got to something like this, where here's a collision, but no corners are inside of any box either way. Here was an interesting case where all the corners were inside a box. That would be easy. But this one started giving me troubles, and I started realizing there's lots of weird ways that we can have boxes intersecting. and some of them don't include corners being inside boxes. And because of that, that made it a little bit trickier. And what I realized is actually I ran out of ideas. I said, there's too many, this can't be right. And then I gave up and I Googled. Okay, well, there's nothing wrong with Googling. You know, there's lots of information out there on the internet. You go ahead and grab it. You don't have to reinvent the wheel every time. And what I realized when I got out there is they said, oh, a lot of the blogs and posts I found said, oh, detecting to see when they intersect is actually harder than detecting when they don't intersect. Which seems weird because these are two sides of the same coin. We should be able to detect one or the other. But just logically, it fits better in our human brains maybe. Maybe if you have a robot brain or an alien brain, your brain works different. But in my human brain at least, it was easier to determine when they did not intersect. And in fact, there's really only two cases. There's four cases, but we can draw them in the two pictures that we've got here. If the two boxes are not intersecting, then one box is above the other, or one box is to the left of the other. I said there's four cases because technically we could also put that as saying one box is below the other and one box is to the right of the other. Those are the four cases we're going to check in a second. Okay, but basically let's say I'm one box and I want to know if I intersect with you. I'm just going to do four checks. Am I to the left of you? Am I to the right of you? Am I above you? Or am I below you? If the answer to any of those checks is yes, then there's no intersection. If the answer to all of those questions is no, I'm not to the left of you, I'm not to the right of you, I'm not above you, and I'm not below you, then I must be intersecting with you. There must be an overlap. And it's weird because this is kind of a negative test, right? We're negatively testing for the intersection by saying, hey, if I'm not intersecting with you, then I must be intersecting with you. That's a little bit bizarre. But once we realize we can take that approach, we see, oh, the number of cases I need to encounter are actually a lot smaller. I guess I didn't quite mention, I could also be above you and to the left of you. If my box was drawn, say, up here, right, then that box would count as satisfying two of my cases. It would be to the left and above. Well, either of those tests then would determine that there's not an intersect. Okay, so let's see how we can put this together now. And I've got this, I'm going to start with this sort of English-wise, okay, and I've just said this English on the previous slide. If my right edge is to the left of your left edge, then I'm to your left. Okay, let's try and visualize this for a second. If let's say this is my box, if my right edge, this is my right edge, is to the left of your left edge, then I'm to your left. If my right edge is to the left of your left edge, then I'm to your left. Okay, flipping those around, and you can test this on a diagram if you like as well. If my left edge then is to the right of your right edge, I'm on your right. That's just flipping it around the other way around, okay? So if I'm on your left and I'm on your right, remember that means no collision, okay? Also, if my top edge is below your bottom edge, that makes a little bit more sense, but maybe let's go back and just check again. If my top edge is below your bottom edge, like this, then there's no intersection, then I'm below you. Likewise, if my bottom edge is above your top edge, then I'm above you. These are my four possibilities. If none of these cases occurs, then there is a collision. That's the case, that's the collision detection that I want to do there. Okay. Now I'm going to show you how in Super Mario I actually done this. I've created a bounding box class that I attach to any entity that needs to do collisions. And for that entity, I will define its x, y, width, and height. Now what you'll notice here is in my tests here, I'm talking about left edge, right edge, top edge, bottom edge. So it might actually be convenient for me in my bounding box to actually store things like right edge, left edge, top edge, and bottom edge. And so that's what I've actually got down here is I've taken the x, y, width, and height that we store, and I am going to store that in my bounding box as well in case I want to access that. But in my test down below, I'm going to use left, top, right, and bottom because that's what my logic up here is saying. And I've just calculated, I mentioned this earlier, I can calculate my right edge by taking the left edge and adding on the width. My left just being the x coordinate, and again doing the same thing for the bottom, the top, plus the height. Remember, plus is down in our web environment. And so this is going to set up just some references to left, top, right, and bottom, which makes it easy for me to take this sort of English logic I put here and turn it into a test. Now, I'm going to flip this English logic on its head because at least the way I've got it here, I want to know when I collide, not when I don't collide. So what I'm doing here is this is going to say if the right is greater than in our x coordinate means to the right. So here I was supposed to say if my right edge is to the left of your left edge, then there was no collision. So here I'm saying if the right edge is to the right of your left edge, then I know this case is not true. So if this case is not true, I'm not to your left, I'll proceed to the next step. The next step is, again, negating this line here, is going to say if I'm not to your right. Notice I've changed this up here. This would be if I'm in this case, or this case, or this case, or this case, there's no collision. So I've changed it to ands now. If I'm not in this case, and I'm not in this case, and I'm not in this case, and I'm not in this case, then there's a collision. And so that's what we've got here. I've got my 4 cases stated, but I've negated those cases by really just flipping this sign around, okay? And then changing my ors between all these or, and or, to ands, basically applying De Morgan's law one time to this big or to create a big and. Now the other thing I could have done, and this is perfectly fine, if you don't like this version of it, you could flip it around, we could do the negative check. I could have a return false on the first line, and all I would have to do is change all these signs, flip them all backwards, and then change all my ands to ors. Again, just applying De Morgan's law to this particular logical statement will give me the negative test, which I could return false on. I don't know why my own logical brain prefers, my test to return true, so I applied De Morgan's law to this logic up above to get this collision detector down below. Now the last thing I want to test, and this is going to be a little bit more difficult, usually in your game, and I'm going to definitely stress this for your game, either circles or rectangles is usually the way to go. Not both, just because both increases the complexity again a little bit more. But maybe you've got a world that's just got circles in it and rectangles and you just need to have both, then that's fine. You can still do circle and rectangle collision. And to do that, it's, as I mentioned, just a little bit more complicated. So let's start out by taking a look. Let's imagine we have a circle and we have a rectangle, and we want to see if they collide. Now, one thing I want us to remember again, that our rectangles are usually stated by our left, right, top, and bottom, or at least our x, y, width, and height. And remember that our circle is given by its center point and its radius. If this circle collides with this rectangle, then notice the center point of our circle must be within this larger dotted box outside here. It must be, okay? Let me put that as a slightly opposite way, the negative way. If the center point of my circle is outside of this dotted box, then my circle does not collide with my rectangle. Again, why is that? Let's take a look. Well, first of all, how did I draw this dotted box? I didn't actually mention that. This is the radius of my circle. So I've taken the radius of my circle and I've just added it to the left edge and the right edge and the top edge and the bottom edge of my rectangle. And now I've got a bigger rectangle. And the reason I've done that is because now I can do a very simple check. And I mentioned this earlier, that checking to see if a point is inside a rectangle is very easy. It's just seeing, is my x between the left x coordinate and the right x coordinate, and is my y between the top y coordinate and the bottom y coordinate. So a pretty simple test to see if a point is inside an axis aligned bounding box or a rectangle like this. So the first thing we do is we create this bigger rectangle by adding the radius on each side of our rectangle, and then we just check to see if the center of our circle is inside that box. And as it says here, if it's not within the rectangle, we're done. We say no collision, we move on. What happens if it is in the rectangle? Well, if it is in the rectangle, we'll notice that not every single circle where the center point is inside that rectangle is technically colliding with the rectangle. In fact, if the center point is like this circle here, where my center point is right here in the top corner of that rectangle, then we can see that when we draw the circle here, it doesn't collide with the corner here. In fact, if we wanted to, we could move that circle down a little bit until its center point reaches this dotted circle. If the center point is inside this dotted circle, then we are colliding with the rectangle. But if it's in this little weird sort of triangular with the circular edge here, if we're in this little region here, if the center point's in here, then there is no collision. So what we do is we do our first test. Is the center point of our circle within this dotted line? If it is, then we have to do a second test, which is usually what we do is we check, is it on the left side, top side, bottom side, right side? So we try and figure out which corner it is. And then we test to see, is that corner inside the circle? So notice that's a point inside a circle test. That's actually technically a circle-circle collision where one of our circle's radius is 0. Okay, and we can do that. So that's very simple as well. We did that. We just looked at that earlier, circle-circle collision. So again, checking to see if this point is inside the circle will tell us if we are actually colliding with this corner or not. Okay, and that's again if we're inside this larger rectangle, but we cannot confirm that we are in a collision because we are in one of these corner cases. So this is technically what we might call a corner case, where we need to be extra careful in checking to see if the collision occurs or not. Because of this extra corner case, this is what adds the complexity to circle and rectangle collisions. So again, it's one of the reasons why we would avoid using both circles and rectangles in our collision detection if we can avoid it. If we can't avoid it, then we have to do this additional extra check. All right, that's all I wanted to say in this video about collision detection. Although now what I'm going to do in the next video is go and show how I've gone and applied this in my Super Mario Brothers, and then we can talk a little bit about collision handling as well. All right, so thanks a lot for watching, and we'll see you in that next video.